Heyo, and welcome back. So, we won't get into how much I thought I was streaming but wasn't live yet. But anyway. So today we're going to talk about working more with the processor. We're going to do something similar to an OS interrupt call, and what the here we'll get to show on the instruction set here. So one of these features is both a hardware interrupt, where a device says, I need to get a hold of the processor and do something special just for a little while. And it's a hardware interrupt. You can also have a software interrupt. And the purpose of it really isn't to do things, asynchronously. But it's a way of encapsulating code that does something special and being able to call it from new code that doesn't have the source of that other code, nor has direct access to the libraries that code was built for. So operating systems, if you create an operating system, you create it in binary, you distribute it in binary rather, and then you need a way to call the functions within it. So another way is also how you would access the BIOS, the basic input-output system. Essentially interrupt calls. You put a particular value in the A register, you put another value in the B register, or what have you, and then you call the interrupt. And the difference between an interrupt call and a standard function call like this is that the function call only has to put the return address where it needs to come back to. That's the only thing it puts on the stack, so it doesn't save anything else. An interrupt call will actually go through and save the status of all of the registers, then do whatever it needs to do, and then restore all of those registers back when it comes back. And that's so that there you can essentially, that in doing that, you're able to have multiple threads of execution even. And we'll get to that. We'll get to maybe a multi-threaded OS in this at some point. That's way down the line. All right, so let's see. Let's go ahead and demonstrate going into a function call, just to show you what's happening on the stack. Now that we can dump memory. Can we though? Well, we'll step through it, and you'll be able to see it, I believe. Yeah, we'll do that. Do we need to make a special program? Maybe not. Well, you'll be able to see it in the stack pointer in the sense that it'll only change by 2 bytes. So let's do that. We'll run our monitor program, and let's put a breakpoint somewhere down in here. If we don't already have one, I think we might already have one. Let's do it just before dump lines. So a halt followed by a no op or no operation is my concept of a breakpoint. Save that. Assemble it. Run it. We have an old copy here. Let's get rid of both so I don't get them confused. Run it. And just run from there. MR FF F0. There we go. We're just about to call the function dump line. You can see here, well, not yet. You can't quite see it yet. You can see our stack pointer is FFFD. So as we load our address, load the 1, and then we're about to call the function. We step into the function. There we go. We moved the stack pointer down 2 bytes, and that's so that we have enough space to store the return address. So here we're going to load the header, and we step into this function, and by doing that we subtract 2 more. And we're trading stack pointer and the data register so that I can loop through things more quickly. Sounds like I'm having, is it YouTube trouble? I tell you, trying to stream to 3 at a time seems problematic. Even though that's supposed to be the service that I'm getting. Anyway, there's the printout. And there's all the data we've stuffed onto the stack from different function calls. So I think what we can do is just inside the, just here, let's do, see this, we'll do POE 0. And what that'll do that before the dump line setup. Right here, this should copy our stack pointer into our data register and add 0 to it. And what that should do is cause it to be displayed here for us, so we can see the value on the stack just before we call dump lines. And then inside dump lines, wherever you go, Mr. Dump Lines. Here, Mr. Dump Lines. Dump lines. Minimize that. There we go. As the YouTube catch up, we'll see. Not dump lines. Yeah, stack dump. That's not done yet. Not dump lines. It's DRAM dump. That's the one I'm looking for. There it is. So just as we get into DRAM dump, we're going to call POE 0 again. And that is going to be okay, because right here we're going to load DR register again anyway. So with those extra ones, we should be able to temporarily look at the stack as we go. Cool beans. Don't need that now. See. Output file not updated. That's new. What's going on there? Oh, undefined symbol. Util functions. Oh, stir. Constants are always in hexadecimal. In this system, anyway. 539. Oh, the other one. There we go. That's a better compile. All right. Come on, 1, 2, 3, 4. So we halt. Now we're going to load this value into that value and add 0. And now we can actually take a look here at what we have on the stack. Ooh, it's a mess already. But our stack pointer is all the way back up here. So now when we load dump lines, And we're going to call DRAM dump. Do that again. Now you can see we're 2 more bytes down. And these are the locations that we're going to come back to when we're done with this function. So here we're going to, let's go ahead and run from there. There we go. So now for an interrupt function, let's see, what do we want the interrupt function to do? Just make it do something simple, like say hi from interrupt. Let's do that. All right. So we're going to do it inside the monitor. See what functions we got left to do. We have to print boot banner. Let's see, maybe inside the help function. So what the help function is going to do, let's see. Typically, this would be done for basic input-output, or in the early days to draw windows and things like this. Let's see. Well, even though these instructions here allow me to write directly to the I/O ports, and these let me read directly from the I/O ports. Let's just do that in a interrupt so that I don't know. Read or write I/O. For now, let's just make it put something on the screen without blowing the system up. How's that? So in between these 2 places, we are going to first, let's see. We need to, first off, we need to set up an interrupt function. So we want to define our Q funct and let's see, get which one of these is which now. What? No zoom? No zoom. Oh, not on it. That's why. All right, here we go. Q1 raises software encrypt 1. Q2. Really? Is that even what they're called? Oh, they're not called that anymore. What fun. I'm not even consistent in my own document. Oh, there they are. Yeah, they. I'm getting old, forgetting my own instruction set. You know, what are you going to do? Here's IRQ1 and 2. So by executing these instructions, we call the interrupt. In fact, why don't we do that at the top of the program? I really just don't want to start a second program for testing interrupts because I'm lazy. But we'll just do it at the top instead of, let's do that. Instead of doing the print of the boot banner, let's take the boot banner and put it in the interrupt function. Where did I leave the interrupt function? All right, let's print that off here. So let's do that. Define our interrupt function, and all our interrupt function does is one function. Grants the boot banner. And we might as well call it our Q1 funct. And then after it does its thing, it needs to return from interrupt, which is IQR, I believe. So IQR, is that what it is? IRQ is clear. Raise clear, unmask, and mask. Yeah, so raising it is, yeah, that's raising the hardware. What did I do? My return from interrupt function. Oh, RTI, that was what it was. Yeah. Jumps and calls. There's my call. Yeah, return from interrupt. There we go. I knew I had it documented. All right. So that's all we're going to do. We're going to print the boot banner, return from interrupt, and that's the end of that. Not a terribly complicated interrupt. And we place the interrupt much like we place main here. And let's see. I think we're going to have to set the origin at 0, 1, 2, 3. I think it's 4. And then we're going to write the IRQ function. And that should put it in the 4th and 5th byte of ROM. And I think that's the right spot. If not, it'll just reset and do nothing. So it'll be fun to watch. I have to look at my manual here. Let's see. Where's the ROM layouts? You're in here somewhere. There we go. So, yeah, hardware vector, software vector is 4 and 5. And it's typically that. Yeah, whatever. It should be none of that, but this will do it. All right. Don't need that or that or that. Yeah, let's come back to that. All righty. Create back in place. All right. So this says put the address of this function at byte 4 in ROM. And that is, in theory, where we will go when we call the interrupt. We're not doing anything special. We're just gonna not paying attention to what papers passed or anything. We're just going to execute these lines and return. So here in main, first thing we do is raise our interrupt. And to do that, we do IQ1. And this is one of the first times I've ever tested this. So we'll see. IQ1 should get us nowhere. What do you know? IQ1 got us nowhere. We did not print our boot banner. We did not go into here. Dang it. Dang it, Bo bang it. Let's see. IQ1, why is that not working? Well, first off, what was it? 88 was the instruction that we just attempted to execute. And not surprisingly, 88 is IQ1. So the assembler was correct. Let's see. IQ1 88 is looked up in the instruction sequence map. And 88 IQ1, sure enough, it has flags, and the 8 is a flag and the 15 is a sequence location in the sequencer, and 15 is the sequencer, which is supposed to be system operations, which did nothing. That's not really supposed to be system operations. It's supposed to be way down here. Where'd you go? IRQ. Should be C0. Who's got C0? Not that C0. Huh. Yeah. Looks like we have failed to map these correctly. So instruction 88, IRQ1, should be not 0815, but rather 08C0. So C0 in the sequencer, just all the pushing of the values onto the stack. Well, let's see. That should do it. So now our instruction is actually mapped to the sequence in ROM for an interrupt. Let's give it a try. All right. So actually don't need to reassemble. Just need to rerun because I've already modified those instruction tables. And call IQ1. Come on, IQ1. And IQ1 for some reason puts our instruction pointer at 6854. Well, that totally makes sense, huh? Why would that be? That is totally wackadoo location. And of course, there's nothing but no ops from there, so it's just going to circle around. All right. So let's step the sequencer and see all the things it's doing think I can look at the sequencer while I'm doing that. Well, after I start that, so. All right. Whoops. Wrong button. There we go. I said 8C0 is the sequence map location. Let's see. So that should have started with this. Sure enough, that's the sequence for C0, C1. So we're pushing T on the stack. Pushes P and TIR. And there's the instruction pointer. So it's putting P, I, R, D, T, B, which is 0, A, which is 0. It's putting all of these values onto the stack. Right? And that's all well and good. Sequence D, 0. So we got through all that. IPU read 65. What in the world is that? One equals 0. P Yeah, so this is supposed to set up the IP P equals ILUI. That's probably wrong. Where did it get 65 from now? P constant. Oh, yeah. Chat a little bit longer. Let's do that again. All right. So the sequencer C0. And this is where we push all of the values onto the stack. And that seems to go correctly. One, two, three, four, five, six, seven. Yeah. I equals 0. P equals ALUI. Not B4. Also, right after that, P equals a constant. Hmm. So what this was supposed to be, I think, what it was supposed to be, this should have been made P8, which isn't what I really want. Um, all right, sequencer. Ah, too fast. A little too fast there. CF. Number CF. A, B, C, D, E, F. Yeah. So this now looks a little weird. P equals ALU immediate, and then P equals constant. So that's our sequence, 400. So take a look, 00. This nibbles the 4 ALU function input expression. Is use ALU input constant. Right. And then fill time. Use value input constant, and that is 0. All the other bits are 0. So you input constant in the sequence map. ALU input constant, and that would be that. So that would come 8. At which point he essentially teed up. Not how that's supposed to work, I don't think. I thought that interrupt was tested. I don't think that's how that's supposed to work. Oh no, here it is. Yeah, system command bit. Oh, so that I need the ALU constant. So this should act as a system command bit. The system command bit should make it IRQ1. There's the 8. So is my simulation not correct? It's the beauty of having this as both a 90s style emulator, which goes very fast, and the full simulation. So let's see. Well, first off, let's load an image here. Let's see. VO4. So now it's kind of hard to see here. Let's zoom in. Yeah. So this is the start of the program main. Then this is the hardware interrupt, and this is the interrupt function that I'm going to call IRQ1, the software interrupt. And we can see that if we look at the symbol table, we should see our IRQ function in here somewhere. There we go. IRQ function 1, and it is located for sure at 04E5, which in Little Indian is E5 or 5E04. So that's good. So that is in the correct place, I believe. So let's see. Get that all centered up. So let's single step through this, shall we? Reset. As we single step, we clear out our registers. Eventually, we load up that location into the instruction pointer. There we go. And the very first instruction is 88. And easier to read. Now, what we want to happen Now what we want to happen is get to sequence through it's still 0815 in this sequencer. So we've got to reload the sequencer. All right. That's it. Setting up again. Our address. Load instruction 88. There we go. 88. Sequence counter 16. You're not supposed to be doing that. What in the world? Sequencer. Not a sequencer. It's a sequence map. But we might need to. Should have loaded them all up anyway. There's a sequence map. Now back to this. Reset. Run through all the steps. Get our starting address. Load 88. Now it says C0. Well, easier to read like that even. C1. This is where we're going to start. Start loading stuff into the stack here, but everything's 0, so it's going to be fairly boring. All right. CF in the sequencer. Zero out that. I see the 65 is left over because it's just not being read. We read the 40. Where we read the 40 from? Read from T. There's 68. Wow. This is not doing at all what I thought it was doing. Now we're 6841 reading a bunch of no ops, doing nothing. Well, the fact that it behaves the same in both should help us debug what the problem is. So in the sequencer, the IRQ, which I thought I tested for at least a hardware IRQ. T equals constant. This is supposed to be, so this is where the problem is. It's supposed to be a constant of 4. 4? 1, 2, 3, 4. Well, 0, 1, 2, 3. So yeah, it should be a constant of 4. Does that mean my constant's wrong? Is wrong? Let's see. So the constant's wrong. It's in this guy. See, he's got 0, 1, 2, 4, 6, and so forth. And the address is the yeah. So what would put the constants from is wired to these 2 bits. Those 2 bits of the control word are I thought I'd have a 3 instead of 4. It's a 3rd memory location. Sequencer. Let's see, it's 8 400 0 8 UNR high and then F40. Operation. What happened? Let's see. Get all this lit back up. Eight. At no point in this sequence at this point D1 D1 that is supposed to be putting out 4 from the constants ROM. If not that step, it's putting out 40 from the constants ROM. Why is it putting out 40? Remember the constants wrong. So put enable the address bits. No, 1000, which is 8. Down 18. Want 3. So here in the sequence map, RQ1 and 3. All right. Sequence map. Load. All right. So it should be the same thing. The sequencer should be the same, really. I want this to be the same for each of the interrupts, hardware, software. So I want it to be the sequence map that decides which one we're doing. Let's see how that plays. Reset. Run through all the setup. Get to our instruction. 88. Store off our values. One. There we go. That's a 4. Now let's load 4. There we go. Now we're looking at our address. Yay, there we go. Yeah. Tight. Supposed to read 5E into T. Increment the instruction pointer, read full forward here, read 5E into there. And now we're at our, all right, cool. Ooh, tight. All right, we're back. So, all of that should be corrected now. Let's get back to our program. Back to our originally scheduled program. All right. And run again. Single step. There we go. We called into our function. We can call print 1E as usual. Whoopsie. Seems like we have an error. We seem to be repetitively calling ourselves. Where are we? Printed that. So let's see. That's a problem, eh? So we call that. Oh, I do believe I have to clear the interrupt after I'm done dealing with it. So that's a IQ clear, I believe. IQC. And then return from interrupt. That should do it. Control 7, we built. And F7 we run. We called in the function correctly. Print banner. Let's see. Nope. What in the world? All right. QC, that should be IQ interrupt clear, yes. IQ clear. Hmm. Mask, unmask, clear, raise. Why am I not clearing? Let me guess. We didn't implement that yet. So IQ clear. Clear the interrupt. And IQ clear. Well, again, we worked this far. Let's see if we behave on the simulation. Load the new program. And go up to here to run it. And run it. We do. We print. It's god awful slow. All right, we're going to simplify this a little bit more because otherwise it's going to take too long. Yeah, it's doing the same thing. It's just cycling around. All right. Let's happen in the simulation and the emulation. Well, I got a bunch of these running too. Kill. So that shouldn't have been anything though. All right. You are an amazing man. Why, thank you. Well, thank you there. Axams. Sorry if I mispronounce it. So let's see. All right. So there's our IRQ pending. So let's just walk the step. Well, first off, let's check our Let's check our sequence map. Sequence map, that ain't you. Here's a sequence map. You're a sequence map. And our instruction for IR clear is 3.3 and 3.3. Again, that's not, well, it's calling function 3 of the system functions. System operation, which is IRQ3, so that all lines out. Now we go into the sequencer for 15, which just expresses our operation, which should clear that trigger set. Let's see. First off, let's simplify this a good bit. We are not going to do these two long things. Instead, we will just do write one from EEPROM, and we'll just put the character asterisk out. Sounds good. Simpler. Builds nicely. See if it runs. If we just hit F5, screen full of asterisks, eh? So that's what we're going to find out. Why is it not clearing the interrupt like it's supposed to? If that's what's happening. So, yeah, let's see. See if it's interrupt clear. We'll find that out pretty straightforward in the simulation. load our new program. And let's just reset single step through. Reload our beginning location. Instruction 88, which stores off all our values on the stack. And then reads the interrupt location, which probably does D1 with the character 2A. There it is out of our output port. And if we look up here, don't have an interrupt pending or anything. And then these are set. That's what I thought was happening. These weren't getting reset. All right. Well, that's the extent of that instruction. Now we're calling 33 the interrupt clear, which (315) inside the sequencer. 315. Q raise is still high. So RQ clear, unmask and mask. Interrupt clear, mask and mask. Looks like it's masking it. It doesn't seem right. RQ pending. All right. So this is a return from interrupt. Well, you know, maybe that's what we're doing. Maybe we're just not returning to the right location. That would be really bad. But it could be off by 1, and we'd just be cycling around. Let's see. All right, so here we're going to be reading back all our information from where it was, and here's our return address, 0462, 0462, which is 88. Which means we go back and do it again. Yay! 0462. I need to increment my instruction pointer 1 more so that we go back beyond. So it is the return instruction that is the glitch. And maybe I don't need the clear since it's not a hardware interrupt. I didn't envision that we would need a clear for a software interrupt. But the problem is in our single sequencer, sequencer RTI. So RTI pops all the values off the stack. Goes to the saved address, loads the instruction register. We need one more step before this, which is an increment. EE is outputted in ROM, and the 4 at the tail end of that is toggle DRSP. But we also need to increment the IP address. So 2 and 4 can be set. Two and 4 can be set in the same nibble. And so that would increment our IP address. It is the last one, right? Yeah, the last one is 4. Yeah, so let's, if we add flag 2 to flag 4, we get flag 6. And that should increment our instruction pointer one more before we load. That way we come back to the next instruction, not the same instruction over and over and over and over again. So again, that's our sequencer map. Should be automatically fixed. When we run next time, just hit F5. Yay! Looks like that's good. Exit out of there. Go back to our emulation. We need to load the new sequencer image. Then if we go all the way up to the computer monitor version, reset, run. Oh, that ain't right. How did that not load? Should have loaded here. Let's see. Sequencer. Well, it's a sequencer that I changed, right? Yeah, I changed this value. And that's saved. And we load the image here. Sequencer run, yes. And hell, it's even said if supposed to be EE. Yeah, 86. There it is. You can barely see that. Sorry. But there it is in the sequencer map right there. Well, maybe I do need to clear the interrupt. All right. Load the program image as well. All right. Load up all that. Get to the start. Call our interrupt, which stores everything on the stack. The address of what to do. Writes out a character. Carry 3. Supposed to be interrupt clear. I thought we got rid of that. Did it not rebuild? No, 33 is a return from interrupt. All right. There it is returning. We load our old location. He supposed to hear with our instruction pointer, and it did not. A lot of looping around. We call it into the function. Write the value out here. Return from the interrupt. We read back all our values. E. You dang it. Double hit the button. Get back up here and get back to the end of it. Write values out. Write our value out to the output port. There it is. Now we're returning from the interrupt yet again. Read back our values. FD. Did not increment our instruction pointer. We might, well, we just loaded it. Just loaded it back. So our sequencer do we need a whole nother instruction? That's kind of a pain. So EE in the sequencer all right, so EE in the sequencer presents this. This goes out. There's our increment instruction pointer. There's the increment line. So coming back. EC. So much easier for me to see than you guys. EC. ED. I think it's because no, that's fully loaded. We got the 6.2 in there. What is this? That's the load line. Load the low byte. There's the increment. Huh. Why is the increment not working? Hmm. Why is the increment not working? Well, that's rather annoying. Let's see what we got space in our sequencer. Yeah, well, no, that's EE and EF. Yeah, EE, EF, and then F0. Dang it. What do we do? It works here. It works in the emulation, but it doesn't work in a simulation. And I think it's because NIP toggle DRSP. That should be fine too. Those shouldn't really interfere with each other. And let's see. Put that back to 4. And if we put the 2 in here, maybe that'll work. Give it an extra clock cycle. It should also work. Let's see. So sequencer, reload the sequencer ROM. Come back up here, reset. Single step through all the startup. And we're calling our interrupt, saving all our values. And we do what our interrupt is supposed to do, which is put that character out on the, put the character out here. Now we're going to return. There's E0. Oh, we did load 6.2. We also increment at the same time. Load and increment can't happen at the same time. But it was the next. Put enable low, I'll put enable high. Increment. So I don't have any space in the sequencer to add the command. That's where it's loaded. What do we consider T disposable? Even in an IRQ, this is often the case. Sometimes not all registers are saved for the interrupt, and that might be due to something like this, where I don't have space in the sequencer. Although, let's see, that's D0. Maybe we can do it that way. D0, that'd be good because there's only one instruction that uses this address. So that's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9A. Let's back it up just one. Let's start this at DF. So DF in the sequencer, that means this is going to be ED. And we're going to have a whole IP++, right? So let's just do instruction pointer ++, and has its own standalone byte or word command. There we go. So let's just add one in here, and that should be all good to go. And the sequence map 33. That's IRQ clear is 33. The return from interrupt is here instead of E0. That is going to be DF. There we go. Get a little squeeze a little space out of the sequencer. And that's good because that's the only one address that needs to change for that. So new map, new sequencer. First off, let's do a quick check that it runs in the emulation. That's good. Only ran once. All right. Now let's go into the sequencer logic. We need ourselves a new sequence map, new sequencer. Go back up to main, go back up to the whole computer, reset, and run. Yay! Let's show you, zoom in on the success. Further still. Oh my God, this resolution is for sheesh. Really need to upgrade to full high def for these images. It's just too complicated. Especially this one. I don't think you can even see that on the 7 some odd resolution, right? Comment in the comments if you want me to spend more money to get higher resolution. All right, so that's the basics of our interrupt routine. And let's see, let's go ahead and make it big again because it'll be interesting that way. Now then, we managed to do that and save the T register while we're at it. Now, the way this would really be used is you would do something like LAE, it's say, the character B. We're going to load the character B into the A register. Then we're going to call the interrupt. And then in here, we saved off all the registers. T is still trashed, but I can get it off the stack if I want it. But A should still be what A was before the call. So we want to check if it's A equals B. And so to do that, or rather A equals this function or this character. So we're going to LBE B. So that loads into B, that character B. I should really have something else, I guess. And then we're going to MBA, which is take B equals B minus A. And then we're going to jump a short distance if that is 0. If you take one value and you subtract another value from it and they're the same, you get 0, right? And anything other than 0, they're not the same value. So in this case, it's not the same value. We're going to go and do the next thing, right? If it is 0, then we're going to go through and print the boot banner. And so let's see. We're going to jump, if this is not, to IRQ1 to dot next function. We'll just call it dot next. And otherwise we're going to fall through. We're going to print the boot banner and return. So I got to define IRQ function next. And if we wanted to, we could return early, right? We don't have to have a single RTI call. So if it's B, we'll subtract B from B. If it's 0, we're going to fall through. If it's not 0, we're going to jump to next. Now we're going to wonder what else could it be, right? So LBE, I don't know, let's do asterisk. And so we could tell it asterisk. Thus, we only want to print one asterisk and a character return, right? So we're going to load asterisk into B. Again, MBA, subtract B and A. Jump short if it is not 0 to IRQ1 funct dot exit. Or I guess RTI. All right. And so we define IRQ1 funct dot RTI and we return from there, and then otherwise we are going to fall through again with the asterisk, and we're going to go write 1E, that asterisk character, and then we're going to write 1E, the character return. I think it is. Let's see, string lib or string lib. Maybe it's string lib. Yeah, there we go. There's character return -cr. TAC-CR, I should say. All right, so that's the character return symbol. And then that should fall through and we'll return. So we're going to do one of the two, right? Here we're going to print the full boot banner. And then, let's see. There's a clear function. There's the memory function. Well, here's the help message. We'll do the whole help message. Just your carriage return there. And then we'll test it out here. We'll do LAE asterisk and then IQ1 rather. All right. So that should show a little bit of variety. Compile, simulate. Let's move this back to about there. All right. Step in. We're going to load the B character into A. We're going to interrupt 1, which sure enough, we get there and we still have that value in A. So load the value into B, subtract the 2, our non-zero. Oh, yeah, because it was 0. What do you know? We load the boot banner, and we call that, and we return. And that should be all that is. Bonus, okay. So now, if we print the command, the question command, that didn't seem to go right. Let's see if we get into this point. Alt no op in there. And then compile, run, interrupt 1, sure enough. Print the boot banner. Sure enough, we got to function next. And it did LBE asterisk 2A 2A. They're the same. There's our asterisk that we printed. We did a character return, and then we return from that. Ah, interesting. I kind of overwrote myself. Huh. That seems kind of odd. Wonder why that is. Let's see. Change this back to boot banner. Or no, that's not it. If we go down here to our help function, change this back to boot banner. See how that plays. All right. And let's just let it rip. Potato chip. Right? Well, that seems to have been fine printing it out. This is a carriage return line feed problem. I did just carriage return. Yeah, that's true. I did just do carriage return. I didn't do line feed. So, yeah, one of my pet peeves of systems. All right. Well, that's looking good for now. We did our main functions. We figured out our software interrupt. Now we can do things like read from a port, write from a port, something along those lines. And I think we're good for now. My rear is getting a little cramped. So thanks for joining me. Please be sure to like and subscribe and check out the EUP5108 series. We've got a whole set of documentation regarding this virtual processor. 8-bit, we go from the electrical diagram or electrical simulation all the way up to a assembler and a 90s style emulator. This is all roughly based off of the 8051 microcontroller. That's why I called it the 5108. So anyway, thanks again for joining me. If you stayed for a little bit, thanks at all. We'll see you next time. Bye.